Welcome to Lesson 3, Part 3. This is the final lesson in our course on topology. Let's talk about the shape of blobs. So, when we named this course at the beginning, we called it Giving Shapes to Blobs. And what we really had in mind when we came up with this title was the idea of giving topologies to sets. So a topology on a set will tell you its shape. And when two spaces have the same topology, the idea is that they should have the same shape. So what does it mean to have two of the same topology? Well, let's take a look at an example to get an idea of what I'm trying to get at. Let's consider two topologies on the set consisting of 4 points. So here are the two topologies. I have the red one and the blue one. And the red one consists of 3 open sets, the empty set, the set containing everything, and one open set which consists of this point right here, just 1 point. Okay. And then in the blue topology, I have the set containing everything, the empty set, and also one open set which consists of this point right here. Okay, so at first, you might take a look at these two topologies and you might think, well, those are different topologies because in one case, I have this point which has an open set around it, and in the other case, I have this point which has an open set around it. But the sort of placement of these points was kind of arbitrary in the first place, right? I could have had the points like this. I could have had the points like this. Who's to say that, when I looked at this topology and when I looked at this topology, the points didn't all sort of rearrange themselves by rotating 180 degrees? Then this would be the same as this, right? When I have a shape and I rotate it around 180 degrees, I think it's still the same shape, even if it looks a little bit different, right? If I have a triangle and I rotate it 180 degrees and now it looks like this, it's still a triangle. So topologies are I want to say that topologies are a bit more flexible in that they don't have to be exactly precisely the same elements, but as long as the sort of open sets look the same, then I should be talking about the same shape. All right. So I need some notion of what it means for two sets to have the same topology. But before I can define that, I need to first introduce a couple of concepts. So the first concept is the concept of the inverse of a function. So let f be a function from x to y. Then f inverse is defined as a function from y to x such that f inverse of y is equal to x if and only if f of x, oops, there's a typo there, is equal to y. All right, so the idea is that f inverse is going to be the reverse function of f. Let's take a look at an example of this. So let's say I have two sets, the set apple, dolphin, paper, and the set ABC, and I have a function f from apple, dolphin, paper to ABC. Let's say apple could be sent to B, dolphin is sent to C, and paper could be sent to A. So this is where f sends the elements of my first set to the second set. Okay, so now let's consider f inverse. So remember, f inverse is just going to reverse what f does. So where does f inverse send A? Well, let's take a look at f. F sent paper to A, so we just reverse this. And now f inverse is going to send A back to paper. F inverse is going to take B and reverse this arrow here. And so it's going to send B to apple, and it's going to send C to dolphin. All right, so here's an example of f and f inverse. But you have to be a little bit careful. So let's take a look at the following. So careful, not all functions have inverses. So for example, let's take a look at the following. So what if I have f, which sends apple to A, dolphin to A, and paper to B? Well, let me try to reverse things, right? So I could first think about what's F inverse of A. Well, I need to reverse the arrow that goes to A, but that's going to be both apple and dolphin. So I'm not really sure where to send F inverse of A. And I can take a look of F inverse of B. Well, this one's okay because it only gets mapped to from paper. So F inverse of B should just be paper. But what's F inverse of C? So again, this one is tricky because nothing gets mapped to C, so I can't reverse an arrow that pointed to C. So again, I don't know. Careful, not all functions have inverses, clearly. In order to be invertible, each element of Y must have a unique element in its preimage. So this is shown here, right? The problematic elements were A and C because A had 2 elements in its preimage and C had no elements in its preimage. So I need each element to have one unique element in its preimage in order for the function to be invertible. All right. What I need is bijection. A function f from x to y is a bijection if it is both injective and surjective. Now, injective means that no 2 elements in x get mapped to the same element in y. So this will prevent the problem that we had with the element a in the previous slide. And surjection means that every element in y has a preimage in x, and this will prevent the problem that we had with the element c. So if a function is a bijection, it'll satisfy both injectivity and surjectivity. And if a function is a bijection, it will be invertible. And with that, I think we're ready to look at our main definition for this lesson. The big definition is the definition of homeomorphism. So a function f between topological spaces is a homeomorphism if it satisfies 3 things. 1, f is a bijection. 2, f is continuous. And 3, f inverse is continuous as a function. So because I have that f is a bijection, it will be invertible. So I have f inverse as a function, and I want to make sure that both f and f inverse are continuous. The idea of this is that if f is a homeomorphism, it will biject elements and open sets. So it will be able to match up elements in such a way that open sets will correspond to each other. And if a homeomorphism exists between 2 spaces, then they are homeomorphic, which means that they are equivalent as topological spaces. So when I look at a topological space and I wonder what is the shape of this space, the space is going to be given by the topology. And when I have 2 different topological spaces, I'll know that they have the same shape if there's a homeomorphism between them. All right, so let's take a look at some examples. So remember, we wanted these 2 topologies to be the same. So let's take a look at what happens. So let me try to find a homeomorphism that goes from, let's call this one x, and to this one y, all right? So what I want to make sure is I want to make sure that I'm sort of making sure that the open sets will correspond to each other. So what will I want f of a to be? Well, a has an open set around it. So I think I'm going to send it to D in order to keep that open set. Okay, and what am I going to do with f of b? Well, I don't think it really matters, so let's just keep it the same. F of c, let's just keep it the same. And f of d, well, I can't send it to D because I've already sent a to D, so the only thing left is a. All right, so now I have to find my function f. let me define my function f inverse. So now I just need to reverse all of these equations. So f inverse of A is going to be sent to D. F inverse of B is going to be sent to B. F inverse of C is going to be sent to C, and F inverse of D is going to be sent to A. All right, so now I've defined my function f, and the question is f a homeomorphism? So I need to make sure that those three things that define a homeomorphism hold. So the first thing is f continuous? Continuous? Oh, sorry. The first thing is f bijection? So is it a bijection? It's a bijection if it maps each element to a unique element and it covers all of y. And so I think we can clearly see that each element is mapped to a unique element and every element of y has a preimage. So we're good here. It needs to be continuous, meaning that preimages of open sets are open sets. So let me take a look at the open sets in Y. So there's one open set, which is around D, and its preimage is A. So F is continuous. And is F inverse continuous? Is continuous is the final requirement. And let's take a look at the open sets in the image of F inverse. So the image of F inverse, remember F inverse goes from Y to X. So I need to look at open sets inside of X. And so I see that there's, one interesting open set. It's the one around A, and its preimage is D, which is contained in an open set. So F inverse is continuous. So the answer to this is yes, F is a homeomorphism, which means that these two topological spaces are homeomorphic or equivalent as topological spaces. Cool. Okay, so this example was maybe a little bit easy because, they look very similar. Let's take a look at a slightly more complicated example. So consider two sets, 0, 1, and 1, infinity, with topologies whose bases are open subintervals. So we have 0, 1, and we have 1, infinity. So those are our two topological spaces that we want to think about. And now consider the following map. So f of x is equal to 1 over x. And the question is this function a homeomorphism? Well, in order to figure that out, I need to check to see if it's three things, right? So the first one is it a bijection? Well, what I need to make sure is that it's injective and that it's surjective. So injective means that every element in 0, 1 gets mapped to a unique element in 1, infinity. So let's say I have two images, right? F of x and f of y, and that these are equal, right? If the map is injective, then x has to be the same element as y. So if f of x is equal to f of y, that means that 1 over x is equal to 1 over y, which means that x is equal to y. So yes, I have injectivity. Now, is it surjective? Well, in order to be surjective, I need every element in 1, infinity to have a preimage. So is there any element in 1, infinity that I miss? Well, any element in 1, infinity, so let's say I have x in 1, infinity, then is x equal to f of a for some a? Well, yes, right? If a is equal to 1 over x, then f of a is equal to x. So we have surjectivity, right? No matter what element I choose in 1 infinity, I can always find some element between 0, 1 that gets mapped to it. So I have surjectivity, I have injectivity, so I have bijection. All right. Now let's take a look at the next thing. So the next thing is f continuous? Right, what does this mean? I need to check to make sure that open sets get mapped to open sets. Or I need to check that, or rather, I need to check that the preimages of an open set is an open set. So let's think, let's suppose I have an open set in 1 infinity. Then it has to be generated by basis elements. So let me check to make sure that the preimages of my basis elements are open sets. So my basis elements are going to be intervals. So let's say I have an open set A, B in 1 infinity. Now, what is the preimage of this set? Well, F inverse of AB is going to be 1 over B, 1 over A, right? And so this is going to be an element of 0, 1. And this is open. So F must be continuous. Is F inverse continuous? Well, I can make an almost identical argument. So let's say I have an open set xy in 0, 1, right? Sorry, these should be subset symbols. Let's say I have an open set xy in 0, 1. Then F inverse, so F inverse, which is just F of xy, is going to be 1 over y, 1 over x, which is an element in 1 infinity. So I have that F inverse is also continuous because this is open as well. So what I have here is that the set 0, 1 and the set 1 infinity are homeomorphic. And what you can imagine is taking this set 0, 1 and flipping it over and then stretching it all the way out to infinity. And that's kind of what this homeomorphism is doing. So to some extent, what we're seeing here is that when you take a set and you stretch it, it's still the same shape. Homeomorphisms have a lot of nice properties because they are the equivalence class on topological spaces. So homeomorphisms are going to preserve all of the topological properties of a space. And what I mean by this is if F is a homeomorphism from X to Y, then if X is T1, Y is going to be T1. And if X is Hausdorff, then Y is going to be Hausdorff. If X is connected, Y is connected. If X is path connected, then Y is path connected. And if you think about any of the properties that we've shown you, if X satisfies that property, Y is going to satisfy that property as long as it's a topological property. All right. And as we saw in the second example of a homeomorphism, one way to think about a homeomorphism between topological spaces is the following. So think of a topological space as a geometric object and a homeomorphism as a stretching or shrinking or bending of that object into a new shape. So let's take a look at some examples of what I mean by this. All right, so if I have a circle, for example, I can think about stretching and bending that shape into a new shape. So imagine you take sort of this point, this point, this point, and this point of a circle, and you sort of pull them out towards four corners while sort of trying to keep the other points, you know, relatively closer to where they are. Then you can imagine that you could take this circle and sort of stretch it into a square. And likewise, you can think about taking this square and sort of taking these four corners and sort of pulling them in just a little bit. And that would get you back to a circle. So you can stretch a circle into a square. You can sort of bend, shrink a square back into a circle. And so these shapes are going to be homeomorphic because I can stretch one into the other. Let's take a look at another example. This example is the classic example. Sometimes you'll probably hear, if you continue on in math, lots of jokes about it. So let's say I start with a donut. Then I can take this donut and imagine it's made out of silly putty or modeling clay or something. And I can sort of stretch it out like this, and I can stretch it out, add a little dip in the middle of it, and I can make that dip a little bit deeper, and I can keep stretching it until I get a coffee mug. So a donut and a coffee mug have the same shape, and there's a very popular joke that says that topologists can't tell the difference. But you have to be a little bit careful. So the one thing that we're not allowed to do, so we're allowed to stretch, we're allowed to bend, we're allowed to shrink, we're not allowed to cut or glue. If you cut or glue, you'll end up with different shapes, different topologies, things that are not homeomorphic. So here's an example of something that you can't do. So a circle is not going to be homeomorphic to a squiggly line, because in order to get from a circle to a squiggly line, you have to cut the circle somewhere. And that is not allowed. Let's take another look at another example. So a circle is not going to be homeomorphic to two circles. Why? Again, because in order to get from one to the other, you're going to have to make like two cuts, and then you're going to have two strips, and then you're going to have to glue the strips together to get two circles. So this is another non-example. And you can tell that it's a non-example because you saw before, a circle is a connected space, but two circles is clearly not a connected space because, you know, there's no way that I can get from a point on this circle to point on this circle without lifting my pencil at some point. There's no way to bridge that gap. So if a homeomorphism is supposed to preserve all of the topological properties, then I know for a fact that this cannot be homeomorphic to this. All right, let's take a look at one more example. And this example is a donut and a double hole donut, or maybe an inner tube for one and an inner tube for two. So in order to go from one of these shapes to the other, you could imagine maybe taking like a big knife and or sword and chopping this donut along this sort of circle here. And then what you can do is you can take this chopped shape. We're imagining that these are like solid made out of modeling clay here. And you can sort of shrink these legs in until you get this donut. So these are solid, this is a solid torus, and this is like a not quite an inner tube, I guess. This is more like a donut with 2 holes in it. And in order to get from one to the other, you have to make a cut, and therefore this is not a homeomorphism. All right, so let's finish this up. In conclusion, topology is the study of objects under homeomorphisms. So homeomorphisms are the sort of guiding principle in what topologies are. And to conclude the course, I'm just going to say that we've given you the first steps in this deep and rich field of mathematics. So please go forth and do math, and be careful not to bite your coffee mug or pour coffee on your donut. And of course, try the exercises. I promise that there are a couple of fun ones in the set following this lesson. Thank you so much for your time.